So let's dive into the reduction. So let's take a particular input for the feasible flow problem. This is specified by a directed graph G, capacities along the edges and demands along the edges. Now we need to construct an input for the max flow problem. This is specified by a directed graph, which we'll call G prime, and capacities along the edges, which we'll specify by C prime. Now these capacities don't have to be the same as the original capacities. In fact, we need these capacities to encode not just the capacities in the original graph, but also the demands in the original graph. Let's take a look at a particular example, a very simple example. Here's a small example on 4 vertices. This is our directed graph G, which is our input to the feasible flow problem. Let's specify some example capacities and demands. We've written a pair of numbers for each edge. The first number, for example 3, specifies the demand, and the second number specifies the capacity. Now let's try to create our graph G prime. Well, we want to keep all of this information, so we're going to keep the same graph G, and we're going to add additional vertices to it. So this is going to be our directed graph G prime, which is going to be the input to the max flow problem. So we're going to start with the same graph G that was the input to the feasible flow problem. And we're going to add a new start vertex, which we'll denote as S prime, and a new end vertex, which we'll denote as T prime. So the original S and T will now serve as internal vertices. Now these are the vertices of this new graph G prime. Let's now look at the edges that are in this graph and also the capacities along the edges in this new graph.